Hi everyone. Again, this is one of those circuits I received some time back. I didn't have time to reply, so I thought I'll make a video. It's a very interesting circuit. This circuit is called an Astable multivibrator. It's mainly used for generating square pulses, periodic pulse train outputs. It's a very popular circuit uh, for generating pulse waveforms. And I remember this circuit because suddenly when I saw the circuit, it reminded me during my late teens when I was first reading all these books. So we used to subscribe for this manual called, I think it's still there, Electronics for You, EFY. And you would see some very interesting application circuits built using opamps and timer ICs and all that. Okay, so this circuit, back in the day when I was in my late teens, when I joined my masters, we had YouTube. Back in when I was a student, we didn't have. As an undergraduate in my late teens, we didn't. YouTube was still an up and coming. It was mainly grainy YouTube videos. The lectures that you guys see now were slowly starting to get uploaded when I was in my masters. But I am from a generation where, at least because at that time when the lectures were slowly starting to get uploaded, I was not very keen on circuit design. I had a very different career plan in mind. So I had given up. So I never really got through this education of studying from YouTube videos. So I never went through that form of education. After that, I decided to come back and do work as an engineer and researcher and all that. So a lot of education at that time happened through reading and discussions and solving actual problems and building circuits. So that's how my learning happened. So before that, even when I was in college, we still had access to all simulators, circuit simulators. So yes, so a big chunk of our learning happened through, it didn't happen through YouTube, is all I'm trying to say. So you guys are very lucky. You have YouTube now. The accessibility to information and knowledge is very, very, very good in these times. But what you make of it is entirely in your hands. Okay. So, but I thought I'll discuss this very interesting problem, which I received some time back, and it reminded me of my undergraduate days. And it's a very interesting circuit. And I remember we used to discuss in uh, hostels. So back in the day, if let's say a group of us used to, sometimes I used to conduct classes or teach, and we used to use the back door, our classroom, our hostel doors, and we used to borrow some chalk pieces. We used to pick some broken chalk pieces from classrooms when we were leaving, and we used to use the back of our doors as chalkboards and write on top of it. Okay, I remember teaching like that, and we would have all my friends, batchmates and juniors, sometimes sitting in that hostel, cramped in those hostel rooms, and I used to teach that. So this circuit, when I saw this circuit, it reminded me of that time. So I thought I'll make this interesting video. So the question that was asked here, this is an astable multivibrator. It was not in an astable multivibrator circuit. Usually I'll talk about the circuit in greater detail in a few moments, but it was given where should I connect. So here if you see, there is both positive feedback, and negative feedback, right? I'm just taking the output and feeding it both at the both input terminals of the op amp. So naturally there is both positive and negative feedbacks. The question was, which path should be connected to the positive part, a positive input terminal, and which path should be connected to the negative input terminal. Okay, so here you have a resistive path, and here you have an RC path, a first order RC path. Okay, so which should be connected to the positive and positive and negative input terminals, and does it make any difference? If you flip the input terminals, do you get any different operation? That's what the question was. So I'll analyze both the cases. So I've shown the circuit here. So the RC circuit, the RC path is connected to the non-inverting terminal, and the resistive part, the resistive network is connected to the inverting terminal. So anytime you are given a circuit, the first thing you need to do is to see if this circuit has any steady state behavior. Okay, whether it's an oscillator or not, I'll come to that in a few moments. How do you analyze that? So if you guys already know, I have a set of video lectures on another playlist called Analog Electronics, where I go in much greater detail. I'll talk about a wide variety of circuits in at a much greater detail. But in this lecture series, which is OC, op-amp circuit analysis, I just give you guys just the minimum basic that you need to be aware of. Okay, so I will talk about astable multivibrators and monostable multivibrators and all that in the analog electronics lecture series. But here I just wanted to analyze this from a problem, as a very interesting circuit problem. That's it. So first, when you're given a circuit like this, the first thing you need to see is that, okay, analyze this circuit at steady state, meaning you can treat this circuit like a DC circuit and analyze this. So at DC, capacitors behave like an open circuit, so the circuit reduces to something like this. Now you have a familiar circuit. You guys can easily analyze this circuit now. This has both negative and positive feedback, and I have already discussed how to analyze circuits containing both positive and negative feedbacks. Find the feedback factor in the positive path and the feedback factor in the negative path. If the negative feedback factor is greater than the positive feedback factor, then you can treat it like a negative feedback circuit where you can apply this condition: V plus will be equal to V minus. Otherwise, you cannot apply that, and you know that it's a positively fed back circuit, and in a positively fed back circuit, your output will either saturate to plus Vsat or minus Vsat. That's what you need to see. So in this circuit, you can see the output is fed back to the non-inverting terminal. So this is the positive feedback loop, and this is the negative feedback loop, and the feedback factor is negative feedback factor loop. I'll call it beta minus, is simply R1 by R1 plus R2. So let's call that beta, and this will always be less than 1. On the other side, the feedback factor in this path is equal to 1. So naturally you can see beta plus, the positive feedbacks is more dominant in the circuit. Okay, because the positive feedback is more dominant in the circuit, you can think that, okay, the output is either going to remain at plus Vsat or at minus Vsat, and you can see that. So let's assume we'll start from 0. Let's assume, 0 is a hypothetical condition, but let's assume we start the circuit, all the node voltages are 0. Noise at one node slightly displaces this by delta V. If noise displaces this node by delta V slightly, this node will go to, say, assume delta V is positive, this node will go to plus Vsat. If this node voltage goes to plus Vsat, this node voltage will come to plus Vsat by 2. Okay, so yeah, so this node voltage will come to plus Vsat by 2, and this node voltage V plus will come to plus Vsat, right? There is both feedback is present in both the paths. Okay, see, I'm not applying any external input. When I said I'm displacing this node by delta V, I'm assuming noise offsets. The op-amp's input referred noise could have displaced it. So therefore this node voltage is also subject to changes. So a small change here makes this output node voltage to go to plus Vsat. That's now fed back. So this node voltage would have gone to plus Vsat. V plus would have gone to plus Vsat. And V minus will be at minus Vsat plus Vsat by 2. And the differential input voltage is now V plus minus V minus will be equal to Vsat by 2. Okay, I'm sorry, I've assumed beta to be half. So if this node voltage is at plus Vsat, this node voltage will come to beta times Vsat. So your differential input voltage will be 1 minus beta times Vsat. This is what your differential input to the op-amp is, and since beta is less than 1, this will be always greater than 0, so output will be at plus Vsat. And you can similarly show, if you slightly displace this node by minus delta V volts, slight negative voltage, the output will come to minus Vsat, and the differential input voltage will be 1 minus beta into minus Vsat, and therefore it will stay at minus Vsat for all time. So therefore, if you connect the RC to the positive terminal and the resistors to the negative terminal, then this circuit will not oscillate. It will either be stuck at plus Vsat or at minus Vsat. Okay, it will either be stuck at, it will be purely a positively fed back circuit. It will act like a latch. It will either be stuck at one of those two stable states. It will be either at plus Vsat or at minus Vsat. Okay, there is nothing to disturb its state and change its voltage levels. Okay, So even if you put a capacitor, these changes will not happen instantaneously, but that's what is going to happen roughly. Okay, so that's the analysis of this circuit. This is the steady state behavior, guys. Keep in mind, steady state in the sense very slowly if you apply, this is what you should expect. Okay, so now the next circuit, which is the circuit shown here, wherein I am applying the resistor is now connected to the negative path. Again, we'll do a quick steady state analysis where we will assume the capacitor to be open. You are left with a circuit that looks like this. So the resistive feedback path is connected to the positive terminal. So this is the positive feedback path, and the beta here is the feedback factor is beta, and in the negative feedback path the beta is equal to 1. The feedback factor is equal to 1. I'm calling it beta minus, that's equal to 1. Now here if you see, the negative feedback path's feedback factor is greater than the positive feedback path's feedback factor. Okay, beta minus is greater than beta plus. So therefore the circuit has an overall negative feedback. If the circuit has an overall negative feedback, this node and this node will track each other. V plus will be equal to V minus. Okay, if V plus equals to V minus, what do you get? What is the condition? If you solve this, if I say V plus equals to V minus, what is V plus? V plus is simply given by beta times V naught, right? If this is V naught, this node voltage will be at beta times V naught, and V minus is simply equal to V naught. So if there is negative feedback, these two node voltages will be equalized. If these two are equalized, what do you get? The condition you get is V naught equals beta times V naught. This is not true for any finite values of V naught except when V naught equals to 0. If V naught equals to 0, then you satisfy this condition. So therefore the circuit will come to this operating point where the output voltage will be 0. Then all the input and both the input terminals will also come to 0 volts. So this circuit, if you see, right, the operating point, this I'll call this as the DC operating point of the circuit, is at 0 differential input voltage level. VD equals to 0. This is the point where you are at. But remember, you are at a very high gain point. You are at a very high gain point. Even if I slightly displace this, one of these nodes, slightly displace, then you can either go to plus VSAT or minus VSAT. But because it's a negatively fed back circuit, it will eventually come to 0 volts. That's what you would expect. But what happens is that in oscillators, especially in oscillators, if you see at DC there will be negative feedback. I mean, that's one very important quality for an oscillator is you need to have a stable operating point, and an oscillator will always keep trying to reach that stable operating point. I mean, if what I'm saying doesn't make sense, just think about it like this. Let's say you have a pendulum. Okay, now the stable operating point for this pendulum is you just leave this metal bob, a metal mass, suspended by a wire. Assume the wire is also some metal wire, and if you leave this mass as it is, it will stay put at this point. Now let's say I slightly displace this by some amount. I slightly displace this ball to a different position. If I do that, then what happens is that it will naturally try to come to this steady state operating point. It will try to come to this, but because when it is coming here, it's already carrying some energy. It will move to this point. It will move on the other side. It will be displaced by the same amount. Again, it will try to come back to this point and it will keep on oscillating back and forth. So that's how sustained oscillations happen. And this is a phenomenon that we normally observe even in ring oscillators. You take any simple CMOS ring oscillator circuit, you connect odd number of inverters in a loop like this, you will instantly see the circuit will produce a periodic output. And if you want to analyze a ring oscillator, so let's assume this is my VI and this is your V naught. The inverter's characteristic, the transfer characteristics of a single inverter will look something like this, right? So let me assume an ideal inverter. So it will look something like this. Okay, after a switching threshold, if you apply any voltage greater than switching threshold, its output will be 0, logic 0. Less than that, your output will be logic high. When you connect 3 inverters in cascade, I'm multiplying. What happens here is that a practical inverter will have finite gain, so the transfer characteristic will look something like this. Okay, this curve, if I, instead of a straight line, I show a small curvature, it usually means that the gain is finite. When I cascade 3 such inverters, okay, it will still behave like I can approximate these 3 inverters to a single inverter with a very high gain. With a very high gain, the gain will be a power 3, it will be gain multiplied by 3 stage gains, right? Its gain will be higher, so it will look like, graph will look something like this. It will look more steeper, and it will approximate a pulse, a brick characteristic like this. And then what am I doing here is that I'm taking the output of these 3 inverters and feeding it back. So I'm making V0 is equal to Vi. I'm forcing V0 is equal to Vi. So now if you see, right, there is one stable operating point here, right? The intersection point between these two, with this graph, this is V0 equals Vi, and this is again V0 and Vi. This is the inverters, 3 inverters transfer characteristics, and they both interact at one point. Now that point where they both interact is at a very high gain point. The gain is extremely high at this point. Even if due to noise I displace one of those nodes slightly, what happens? Your output will either it will come to this point, or it will go to plus VDD, or it will come to 0 volts. It will be displaced. Even if I add a slight noise, you will push this operating point to this point or this point. But the thing is, when you push it to either of these points, the outputs will not stay there. Okay, because the stable operating point is at this point, it will try to reach it. And it will, in the process of trying to reach it, it will always overcorrect for it, and then it will try to reach it again, and it will keep on oscillating between these 2 points. Okay, that's what happens in a pendulum as well. It keeps oscillating like this. So you can just take another very simple example. Let's assume you have a metal rod, and then you have somehow balanced your metal bob on a thin metal rod and a metal bob on top of it. You displace it slightly, it will either fall into this direction and stay here forever. There is nothing else to change its position. It will stay here forever. Okay, or it will stay in here forever. It can be either one of these 2 stages. Now this is like a positively fed back circuit. So which is what happens if you have 4 odd even number of inverters in the loop. If I put 4 inverters in the loop, what will happen is that I will end up getting a transfer characteristic that looks like this. A transfer characteristic that looks like this, right? You have 4 inverters, so logic 0, the input of this will give logic 1 here, logic 0 here, 1 here, and logic 0. So it acts like a buffer, a single very high gain buffer. So the transfer characteristics will look something like this. Now if I find V0 equal to Vi, I end up getting this curve. So now if you see, there are 3 operating points here. This is one operating point, this is one operating point, and this is one operating point. So there are 3 operating points. Now if I slightly displace it, let's say noise is displacing this node by a slight amount, you will either end up reaching this point or this point. Now these 2 points, this point here and this point here, are very low gain points. The gain is 0, right? It's almost flat. So once you reach there, your circuit will not have any motivation to change its state. Okay, think of it like this. Once your pendulum falls onto one side, there is nothing to push it, right? Its gravity is already working in its favor and just keeping it on the floor. There is nothing to lift it. So it's the same way here in inverters as well. When you add even number of inverters, you will actually have 3 stable operating points. But 3 operating points, out of which 2 are much more stable. Okay, they are much more stable, and that's why it is used as a latch. These 2 are 2 very stable operating points. It can be either at 0 or VDD. So for an oscillator, you need a net DC feedback. At DC, the feedback should be negative, and you should have one unique stable operating point, but that operating point should be at a very high gain point. And that's what's happening here. If you guys look at this circuit, I'm coming back to the circuit. The DC operating point is where at both the inputs to this op-amp are at 0. So you are in this very high gain region. So this circuit has the potential to act like an oscillator. If I slightly displace it to one direction, it will try to reach this 0, and in the process it might end up being in a different position and all that. Okay, on an average, if you see, it will try to reach 0 volts. The output's average voltage value will be 0. So that's what this is supposed to behave, and we'll do a quick analysis for the circuit. So yeah, so if I want to do this do the analysis for the circuit, you guys need to quickly realize that this half of the circuit is nothing but a Schmitt trigger, an inverting Schmitt trigger. Okay, and the inverting Schmitt trigger with a feedback factor of beta given by R1 by R1 plus R2. Okay, that's your inverting Schmitt trigger, and the transfer characteristics of this Schmitt trigger looks like this. Okay, if the inverting terminal's node voltage V minus is greater than plus beta Vsat, the output will go to minus Vsat, and as you keep decreasing this input voltage, which is V minus, if I keep decreasing it, and if I keep decreasing it further than minus beta Vsat, then the output will go to plus Vsat. So that's what it's supposed to happen. So keeping this in mind, this transfer characteristics in mind, we'll do a quick analysis of the circuit. So I'll assume for the time being that we are at a steady state, so meaning this is at 0, this node voltage is at 0, this node voltage is also at 0. Okay, all the node voltages are at 0. Assume that the capacitor's voltage has slightly changing, it's slightly increased due to noise or some excitement. That node voltage has slightly changed. Okay, because see, remember, you are at a very, very high gain point. So any small offsets in the op-amp or noise in the op-amp can slightly, displace this node voltage. Or I can assume that, there is some small noise which I can model as a series voltage source, and that is slightly changed. And I'll assume that it has changed my output to, it has changed my output to a negative value. Let's assume it is minus delta V, where delta V is a very small but negative value. So what would happen? This node is at 0. This node has gone to a voltage of minus delta V. Capacitor voltage I can assume is at small negative voltage of minus delta V. Instantly your output will go to plus Vsat. When the output goes to plus Vsat, this node voltage will come to plus beta Vsat. And since V minus is at minus delta V, which I'll assume is very close to DC, 0, the output will now stay put at plus Vsat itself. Okay, remember, when I was analyzing the previous circuit, there was both positive and negative feedback I assumed there. But here, if you see, when my output is changing suddenly, because you have connected a capacitor to this node voltage cannot change instantaneously. It will take some time before that node voltage changes. Okay, so that node voltage will stay put at minus delta V. That's why I'm writing it as minus delta V, because there is a capacitor connected to that node. That will not let it change instantaneously. So V plus comes to plus beta Vsat. V minus stays at minus delta V, which is very close to 0. So the differential input is plus beta Vsat. Vd is close to plus beta Vsat. So output will stay put at plus Vsat. So now let's start the analysis. Suddenly, if the output goes to plus Vsat, now you have an RC network, R and C. So this terminal is your V minus. This node voltage suddenly goes from, say, let's assume it goes from 0 to Vsat. So now the resistor will start charging this capacitor, and it will increase with the time constant of RC. From 0 it will start, and it will slowly try to increase to plus Vsat. That's what I've shown here. Let me show it in a different color. So it will try to do this. So V minus is now slowly increasing. V plus is at plus beta Vsat. V minus is now slowly increasing. When V minus reaches plus beta Vsat, that's when your V minus will start becoming greater than V plus. Suddenly, when your V minus becomes greater than plus beta Vsat, your output will trip to minus Vsat. It will be a sudden jump to minus Vsat. So the moment your output goes to minus Vsat, the non-inverting terminal is just a fed back through resistive feedback path. It will immediately come to minus beta Vsat. So this node voltage will come to minus of beta times Vsat. Okay, and the inverting terminal node, the inverting node voltage will stay at plus beta Vsat because it is connected to a capacitor, right? Capacitor's voltage cannot change instantaneously, so it will stay at plus beta Vsat. So now what happens here? You are at this point. The capacitor's voltage is at plus beta Vsat. Now you have a condition like this. You have an RC network. Capacitor is charged to plus beta Vsat. And you have a resistor here. This node voltage has suddenly gone from minus Vsat to plus Vsat. Sorry, it has gone to plus Vsat to minus Vsat. So now this resistor will try to discharge this capacitor till this discharging will happen till this capacitor's voltage reaches minus Vsat, right? So that's what I've shown in this graph. The discharging will happen till the capacitor's voltage reaches minus Vsat. But as the capacitor's voltage starts decreasing, now V minus is starting to decrease. So this node voltage here is now starting to decrease. The non-inverting node voltage V plus is right now at minus beta Vsat. Okay, V plus is a negative voltage to begin with. So V minus is at a positive voltage. So V plus minus V minus is at negative voltage. So therefore output will stay put at minus Vsat. Now the capacitor voltage is slowly starting to change. Okay, it's starting to become negative. It is starting at a positive value of plus beta Vsat, but it has an incentive to go to minus Vsat. So as it is decreasing at the first order time constant, when it reaches minus beta Vsat, this is the point when V minus will become less than V plus. At that point, your output will go to plus Vsat. It will suddenly trip to plus Vsat. It will jump from minus Vsat to plus Vsat. Then the process will continue. So your capacitor voltage will now be at minus beta Vsat. Then it will keep on charging till plus beta Vsat. Then the output will change its state. Then it will start discharging. The moment it reaches minus beta Vsat, then the output will change its states and the process continues. So the waveform will look something like this. So this is your V minus. It will keep oscillating between minus beta Vsat, plus beta Vsat, minus beta Vsat and plus beta Vsat. It will go through a first order charging and discharging between minus and plus beta Vsats. And the output waveform will be a square pulse waveform that will change every time your V minus reaches plus or minus beta Vsat. So this is the waveform you get. Now how do you find the time period? All you need to do is just find out the time it takes for a first order RC network to discharge from plus beta to minus beta Vsat. It has to go from plus beta Vsat to minus beta Vsat. That will be your off time. This will be your off time, T off. Similarly, if you want to find the on time, you just have to find out the time the first order RC network takes to charge from minus beta Vsat. The initial condition is minus beta Vsat and the final condition is plus beta Vsat. The time it takes to reach plus beta Vsat, what is the total time? It's a first order circuit. You can easily solve that using this first order equation. I'll leave that analysis to you. You can estimate the on time to be tau ln of 1 plus beta by 1 minus beta, and similarly off time will be tau ln of 1 plus beta by 1 minus beta. Okay, and it turns out in this circuit, because the charging and discharging path are the same, the on and off times will also be same. And if you add the two, you get the total time period. This is your total time period of your astable multivibrator. It is an oscillator. It keeps oscillating back and forth. And if you guys see here, since the duty cycle is 50%, the duty cycle here is 50%, the average value of this waveform will be 0. Okay, the average value of this waveform is 0. Therefore, it makes sense, right? The average value is 0. Therefore, that's your DC operating point. 0 volts is your DC operating point. So that's what you will get. And this is your overall time period for the circuit. Okay, from this you can estimate what will be the frequency of oscillation. So depending on you have now built a circuit which provides you with a square pulse output. This can be used as a clock input for your circuits. So this circuit is what we call an astable multivibrator. So you need to have at DC, this circuit should have a negative feedback, and that's a characteristic of any oscillator. Okay, especially feedback based oscillators. All such feedback based oscillator circuits should have some form of negative feedback at DC. That's pretty important condition to be met. I'll talk about oscillators at a greater detail. I'm working on some lecture series on PLLs and some interesting stuff about PLLs and oscillators. So in that I'll go into much greater detail and depth. But for somebody who is just learning basic op-amp circuits, I think this is sufficient. So to conclude this lecture, I'll take another very interesting example and then show you guys what happens if I, instead of a resistor in the feedback path, I replace it with a transconductor. Okay, so resistor, if you see a first order if you have an RC circuit, then the output will charge as a first order RC circuit. It will be an exponential charging. It will have some kind of asymptotic charging. If you have a transconductor, on the other hand, GM and C, if you apply a step input, then you will get a constant current into a capacitor. It's almost like feeding a constant current through a capacitor. Therefore, the capacitor voltage can ramp linearly. That's the only difference here. So now if I give you this guy, a circuit that looks like this, to analyze it, what do you think will be your answer for this? Okay, so what I'll do is I'll let you think in this lecture. In the next lecture, it's a very small circuit. I'll quickly post answer for this. Thank you.